Right, this second part of the video tutorial on exercise 4D. I'm just going to look at some extension of 3D operations. I mean, regarding 3D vector. The first one is actually 2D geometry of vectors. Look at this one. It's help you to refresh in case you've forgotten. So if this is a vector A, a negative of vector A is just vector of same length but pointing the opposite direction. Okay, let's try the one more. A negative half of B vector. The B vector is like this. So half of B is a vector, half of its length. Half vector B. But since there's a negative there, it means that this vector is going to point to the opposite direction, negative half of B. And all this is invalid, but this is the vector we're talking about. So half the length of the original B vector. Let's try one more. Try this one. A minus B. If you do a little bit cute trick like this, you find that the difference of two vectors now become a sum of two vectors, and this is A right here, and the negative B, it looks something like this because pointing to the other direction. Okay, look at this again, and so the sum is, so the vector A, at the end of vector A we add negative B vector, and since this is a start point, this is the end point, we joined them, and so voila, this is your A minus B vector, this vector here. See, cool, isn't it? Now move on to the one more questions. This one, and K here is a scalar given to you, and we're going to prove this statement. Let's start by doing this. This is a KA1, KA2, KA3. You call that, you can do that. So the modulus of KA, the vector, is then by formula is a KA1 square, sum of all the squares, each component, KA3 square. And you realize that for each every term has k square as a factor, so there's a common factor, and so we can factor the k square, and you have a1 square, a2 square, and a3 square right here. And so that's it. Not done yet. The law of surd, a property of surd, one of them allows you to do this. There's a property of surd like this, where xy is equal to surd of x times surd of y. So we just basically using that property. It's a1 square, so a2 square plus a3 square. But this would be equal to k, and however by definitions this is actually this. Well, by definition this is actually a positive value of k, so we put this and in the absolute value, and this is by definition is the modulus of the vector A, so proven. And let's move on to one more. Question 8, right? Well, I'm gonna skip ahead because some of the things are actually quite straightforward, and they ask you to deduce this particular statement. So that hence we need to find BD. If you recall, the formula is OD minus OB, right? And so you take the vectors, and you should get negative 2, negative 6, and 6. Okay, and again, it's a good practice to factorize if there's a common factor. You probably realize that the 2 is a common factor. Take the 2, left with negative 1, negative 3, and 3. Okay, let's keep it at that first. Now AC is actually OC minus OA, and the position vectors are already given to you. OC in this case is 1, negative 2, 1, and OA is 2, 1, negative 2 right here. And then so if you finish this, you get negative 1, negative 3, and 3 in fact. And so if you think about it, BD is therefore 2 times this, and is, but what is this vector? This is actually AC. So therefore this is 2AC. And so this is just proven. And I hope you try some other exercise to familiar yourself with the 3D vector.